So before we review a little bit more of integration by substitution, we want to look at a couple of different things here and recognize something to come up with a kind of related law. And then you'll see where this can be useful in the example that we're going to do, because you can see how using U substitution in one case makes it very long. However, if we're able to recognize a certain pattern, it makes our problem very, very easy. Okay? In fact, if we look down at the bottom here, this example, taking the integral of sine cubed times cosine plus sine times cosine, all right, there's two ways that we're going to do this. All right, and that's what we want to try to observe a pattern so that we can do it the easy way. And then we'll also look at it the hard way. That'll hopefully help you appreciate the easy way a little more. All right, so, but first of all, to see that pattern, I want to do 6 different integrals here. We want to do these definite integrals, and in this case from negative pi over 2 to pi over 2 of 2 cosine x dx. Now, what is the antiderivative of 2 cosine x?
Sine x squared? No.
2 sine x.
2 sine x, okay? The 2 is just there for the ride because it's multiplied. And the integral of cosine is sine. So this is 2 sine x. Now what's different here is not the antiderivative, but it's what we're evaluating it at. First we evaluate it from negative pi over 2 to pi over 2. Then we evaluate it from negative pi over 2 to 0. And then we're going to evaluate it from 0 to pi over 2. Okay? Now, what's the sine of pi over 2? Come on, trig experts.
Radical 2 over 2.
Nah, it's pi over 4.
1.
This is pi over 2, straight up. It's 1. Okay? And sine of negative pi over 2?
Negative 1.
Negative 1. Okay? That's straight down. All right? So, when I'm doing this, I have 2 times 1 minus 2 times negative 1. And that's going to give me 4. Okay? What's sine of 0? 0. So I have 2 times 0 minus 2 times a negative 1. Negative negative is positive. 2.
This one's also 2.
And then here we have 2 times 1 minus 2 times 0, which also equals 2. So what do you notice? Is there anything you notice about this one?
It should be 0.
0 is like your mid, so cosine is an even function, so both sides are going to be symmetrical.
Okay. And Tilak actually brought out the key part of this pattern. You'll notice the 2 halves, 0 is right in the middle of the interval that we did, from negative pi over 2 to pi over 2. So if we go half of the interval, we ended up getting half of the area. And the reason that is because, yes, 2 cosine is an even function. All right, what kind of function is 2 cosine? It is even. All right, so it got split into 2 equal halves. If you wanted to see that, it looks like this. All right, we're up here at positive 2. It goes like this on one side, it goes like this on the other side. Pi over 2 is right here. Negative pi over 2 is right there. And the area that we're looking for is this area in here. So you can see the symmetry. Now, remember, an even function is a function where you get the same thing whether you plug in a positive x or a negative x. And there, what that looks like is the symmetry on either side of the y-axis. That's why this works. And that gives us our first observation, which is if we're taking the integral from negative a to a of an even function, you can simply take the integral from 0 to a and double it. Or from negative a to 0 and double it. Either way, it doesn't work. It works. Yeah?
Instead of like negative a to a, if it's two different values, a to b, wouldn't it also work if you took the average of a to b, as long as the function is still even?
If you took the average,
So like say they wanted the integral from 2 to 4 of an even function. That would be the same thing as just 2 times the integral from 3 to 4, or from 2 to 3.
no, not necessarily.
Okay.
No, it has to be something symmetrical. Now, let's say you had a parabola, and the parabola was going from A to some B over here. Okay, and you recognized, hey, A and B are both zeros of the parabola and I have symmetry. You could go ahead and do half of that interval and double that. Okay? But you'd have to be very careful to make sure it's perfectly symmetrical.
Okay.
So it's got to be something that you know, like a parabola or a sine curve or something like that. And you'd have to make sure that it's a perfectly symmetrical interval there as well. Okay, that's a good question though. Okay, so then we had this other function here. Negative 2 to 2, we're taking the integral from negative 2 to 2 of x cubed dx. What's the integral of x cubed?
1/4 x to the 4th.
Yeah, x to the 4th over 4, 1/4 x to the 4th. But again, we're integrating that on different intervals. So we have from 0 to 2 there, from negative 2 to 0 here, and from negative 2 to 2 here. Starting out with the top one, if I have 2 to the 4th over 4 minus a negative 2 to the 4th over 4.
0.
Yeah, that comes out to 0. I have 16/4 minus 16/4. 0. Okay. Now, just based on that, what do you think might be true about the next two integrals?
They're going to be the same. Their absolute values are going to be the same.
Okay, they're going to be the absolute values will be the same. They'll be opposites of each other. Okay, and that's actually what does end up happening. If I plug in a 0 and a negative 2,
You're going to get 4.
I get a negative,
-4.
I get 0 minus 4, so negative 4. And if I plug in a positive 2 minus, and then I plug in a 0,
You're going to get a 4.
I get a positive 4. So yeah, and then if I put those together, 4 minus 4 is 0. And that's because this function x cubed has symmetry about the origin. Okay? Here we have the point 2, 8. And we have the point negative 2, negative 8. And the area we're trying to find here is this. Now understand, when we're just doing an integral from negative 2 to 2, we're getting a net area, not a total area. So the area below the x-axis cancels out the area above the x-axis, and it all goes to 0. Okay? Now what was the type of function that we had that has symmetry about the origin? What's the name of that function?
Even.
Not an even.
Odd.
It's an odd function, okay? It's an odd function.
That was
All right.
close enough.
And this is our rule here for odd functions. Remember, odd functions are functions where if you plug in a negative x, it makes the whole function negative. Okay? And if we're doing the integral from negative a to a of an odd function, it ends up being 0. Okay? Now, this is where, to illustrate this, this is where I said this example has an easy way and a hard way. Okay? What kind of function do you think this might be?
Odd.
Odd, okay? It kind of looks like it. Let's prove it. Okay? Let's prove it. This will be good to refresh our memories here a little bit.
Can we just estimate?
No, that's not good enough, okay? So if I'm going to prove this is odd, then if I plug in negative x's everywhere for x, I'll get the opposite of what's inside the integral right now. Okay? So if I do a sine of negative x cubed times cosine of negative x plus sine of negative x times cosine of negative x. Think about the sine and the cosine functions all by themselves. Sine by itself is what kind of a function?
Odd.
It's an odd function. So sine of negative x is the same as negative sine of x. Okay, so this is actually a negative sine x that's being cubed. Okay, and over here this is a minus sine of x. Now, what kind of function is a cosine?
Even.
It's even. So cosine of negative x is cosine of positive x, yeah. Now, if I cube a negative, I get a negative. All right? So this is just negative sine cubed x. Okay? Well, if I factored out a negative 1,
Can you zoom in a little just to thank you.
if I factor out a negative 1, notice what I end up with. I have a negative sine cubed x cosine x plus sine x cosine x, which that is what I see right there. So yes, this is an odd function. If I plug in a negative x, I get the opposite of the function. So that proved this was odd. So tell me, what is the integral from negative pi over 2 to pi over 2 of that?
0.
It's 0.
That was the easy way.
That's the easy way. Okay? Anytime you recognize relationships, it takes an observation, it takes a recognition of that relationship, but once you do it, it usually makes things easier. So it's worth it, guys, to think, not just dive in and automatically always try the same method, but think about what you're getting, what you're using here. I have a bunch of sines and cosines. Might that thing be an odd function or an even function? Maybe. And you could probably do this in your head faster than we did writing it all down, you know, if you know your identities well enough. Magical?
I don't get like why when you prove that it's an odd function and it's equal 0.
It equals 0 because by proving that it's odd, we proved that there's symmetry on this side and on this side. And if there's symmetry, that means the area above here on the right is equal to the area below on the left. And if we do the integral from one end all the way to the other, this stuff below cancels out this stuff on the top, so it all comes out to 0. Yeah. Okay.
So basically, when we prove stuff, there's no point in actually solving it.
If we can prove something
If
like
we-
that, then
yeah,
yes,
that's what
there's
I mean.
no point in actually. We wouldn't do this and then go back and do it the hard way.
What is the hard
Okay.
way though?
Okay, so the hard way, and this is where I'm doing it this way, number one, just to prove this works, but secondly, to help us review what we looked at before break, okay? The more challenging way here is by U substitution. So let's take a quick look at that, okay? If we use U substitution, the first thing I'm going to do is actually break this up into two separate integrals. Okay, let me write it down, then I'll zoom in a little bit. Okay, so we have the integral from negative pi over 2 to pi over 2 of, I'm going to make this sine cubed x cosine x dx plus the integral from negative pi over 2 to pi over 2 of sine x cosine x. Now, I'm not going to use the odd thing here. That would kind of defeat the purpose, all right? In both of these, the only way that I could actually find this integral by hand would be to identify some inner function u and do u substitution, okay? So, what do you propose we could make the u for this first one?
Cosine. Oh, no, sine. Sine cubed.
Why the sine instead of the cosine?
Because sine is cubed.
Because it's cubed. It's inside of another function. So yeah, that's a good idea. Now, for the second one, it actually doesn't matter which one you made u and which one you know, whether you made sine or cosine u. I'm just going to make the sine u just since we already have done some work here for the first one. So if u is sine of x, then that means du, remember you take the derivative here is du dx, okay, du dx is going to be cosine, and then multiply both sides by the dx. So this would be cosine of x dx, okay? Now, the cool thing about this here is that, let me get something that I can highlight with, it'll work, okay, is I already have a cosine of x dx right here, and I also, in the second one, I have a cosine of x dx. So guess what? I'm going to rewrite both of these functions, okay, as the integral. And notice u was the sine, so this was going to be u cubed du. And this is going to be the integral of u du. Okay? So again, the sine became a u, and the cosine x dx became du. Sine became the u, cosine x dx became the du. Now notice here I didn't bother writing my bounds because these bounds are values of what variable? X. Do I have x's? No. All right, so what I'm going to do first of all here is I'm going to take the antiderivative, which you guys know how to do. The antiderivative of the u cubed is u to the fourth over 4. Okay, and we have u squared over u, or over 2. Okay, however, we need to evaluate those. All right, we need to evaluate those. So what I'm going to do is I'm going to actually put u back in. So it's sine to the fourth of x over 4 plus, and now I can evaluate that from negative pi over 2 to pi over 2, plus sine squared of x over 2, evaluated from negative pi over 2 to pi over 2. Okay? They are, but we're trying not to use that. Just because we're trying, that's one of the things we're trying to like illustrate works. Okay, so now what is sine of pi over 2? 1. What's sine of negative pi over 2? Negative 1. So this is going to be 1 to the fourth over 4 minus a negative 1 to the 4th over 4, which that's a fourth minus a fourth, right?
0.
So that's all 0. And over here, I have it squared, so it's going to be 1 squared over 2 minus a negative 1 squared over 2. A half minus a half is 0. So this whole thing equals 0. Okay? So, we got the same answer, just took a whole lot longer. Okay?
Kind of.
Took a whole lot longer.
So it's still 0, right?
It's still 0, yeah. Our answer has not changed. Okay?
Is there an easier way to do all of it?
All right. So, not really on this. Okay?
I think the second one is easier.
You like the second way? Well, you're welcome to use the second way. All right? The first way, guys, here's the thing. The first way, it's not that you won't be able to do a function necessarily. It's just that it's a whole lot less work. Okay? Now, I want to show you one thing with this last stage, and we're going to do a couple more examples of using the U substitution. And that is, I pointed out to you that the bounds did not apply when we were in terms of U. And I showed you one way that you can handle it. Okay? You can substitute back in the U, so everything's in terms of X, and use your original bounds. There is an alternative, though, and that's what's shown on our next page here. Okay? And that is actually by taking the bounds. You'll notice here's our U substitution, f of g of x times g prime of x dx. And actually plugging those bounds into the U function. Okay? That's an alternative here. If I find, if that's x equals b, and then I plug it into the U, I don't have to substitute U back in after I integrate. I can just use the new boundaries and integrate from that value of U to the other value of U instead. Let me show you here with this one. Okay? What would I let U equal in this case here? Yeah, U is x squared plus 1. And that means du equals
2x.
2x. No, that was it. That's all right.
dx.
dx. Okay, dx. All right. So, not a bad guess. All right. So, hey, we've got the dx. We've got the x. We're missing the 2. How do we get it there? Multiply by 2. And then a half outside. Good. Okay. We're just multiplying by 1, but it makes it look the way we need it to. So now I have 1/2 times the integral of U to the third du. Okay? So here's where the bounds come in. The bounds were originally from 0 to 1, so I'd have U has to equal 1 squared plus 1, and U has to equal 0 squared plus 1. That gives us new bounds. Instead of going from 0 to 1, we're going to go from 1 to 2. Okay? Now we never have to worry about the x's again. We don't have to plug it back in after we integrate or anything like that.
That's easier.
We could just keep going. 1/2 times U to the 4th over 4. And that U to the 4th over 4 I evaluate from 1 to 2. Okay? Some people like this a whole lot better. Some people, they don't like to convert the bounds, so they just like sticking the U back in and have x squared plus 1 to the 4th over 4. And you can use your original 0 and 1. Okay?
So basically to convert the bounds, you just have to plug in the original bounds to U.
Correct.
Okay.
Correct. That's all you got to do. All right.
Perfect.
So now it's 1/2. 2 to the 4th is 16. So it's 16/4 minus 1 to the 4th is 1. So that's 1/2 times 15/4, which is 15/8. Okay? So that's 15/8. Okay? All right, one last one. Here's a case like what you were asking, Tilak. Here's something where there actually is symmetry. And if you plug in 0 and you plug in pi, you do actually get the same value. And I know it's symmetrical because I know sine is symmetrical and cosine is symmetrical. So this whole thing is going to be symmetrical. So technically speaking, we could use the same idea and integrate from 0 to pi over 2 and then double it. Okay? That may be more work than it's worth in this case, but that's kind of what I was talking about before when you were asking. All right, now this one here, we'll go ahead and just find the integral like we have been, but this one, we're going to need to convert this to two separate integrals. The integral from 0 to pi of sine x dx plus the integral from 0 to pi of cosine of 2x dx. Okay? Now, we are going to use cosine of u. The u, in this case, is going to be 2x. Do I need to use substitution for the first half?
No.
No. Okay? The integral of sine is what?
Cosine. Negative cosine.
Negative cosine. Negative cosine. So negative cosine x, we're going to evaluate that from 0 to pi. Okay? So that, and then we'll put the plus because we've got to do the second half of the problem. What's cosine of pi?
0.
-1 minus a negative, what's cosine of 0? 1. So that first half comes out to 2. So we know it's 2 plus something. Okay? So now we have the integral from 0 to pi, and we said that we need to make u equal to the 2x. Now, that means du is 2 dx. I've got the dx, I'm missing a 2.
Multiply it by 2 and then put in the 1/2.
There you go. So I got a half times the integral of cosine of u du. And now I need to change my bounds as well. Okay? So the bounds here, x was 0, so u is 2 times 0, which is 0 for the lower bound. But then it's 2 times pi, or 2 pi, for the upper bound. Okay? So now I have my new boundaries set up. And I've got 1/2. What's the integral of cosine? Sine. So sine of u, and that is evaluated from 0 to 2 pi. Now question here, what's sine of 2 pi?
0.
What's sine of 0?
0.
So this whole thing is 0,
And then the whole thing is equal to 2.
so my whole answer just equals 2.
That's cool.
Okay? Magical?
I don't really get the back one, like
The cosine 2x part? Okay, so just to step through this again here, guys. we have cosine of a function. So cosine of u is what we need to do. Okay? So if we're letting u be the 2x, du is derivative of 2x is 2. So 2 dx. We needed a 2. So we put that in, put the half out here. Okay? So now it's 1/2 cosine of u du. I needed to change these boundaries because this 0 and pi were values of x, not values of u. So I plug in 0 and pi to get my new boundaries to go from 0 to 2 pi. That's what we've got right over here. Now, the integral of cosine is sine. Remember our sine, cosine, negative sine, negative cosine?
Yes, counterclockwise.
If we're going this way, we're going integrals. So the integral of cosine is sine. Then we're able to use the 0 and 2 pi. We don't have to plug the 2x back in because we converted these instead. So sine of 2 pi is 0, sine of 0 is 0, so that whole thing came out to be 0. Okay? Any other questions? All right.